Hello, my name is Preston Landers. This is a presentation about a software engineering paper called FireDroid, Hardening Security in Almost Stock Android. The authors of this paper are Russello, Jimenez, Nadiri, and Van der Mark of the University of Auckland in New Zealand. This paper is about a system called FireDroid that lets you enforce security policies on any arbitrary Android app with a much greater degree of control than with a standard Android permission system. This presentation is also based on a related work called RetroSkeleton, Retrofitting Android Apps by Benjamin Davis and Hao Chen at UC Davis. Both of these papers present a system for controlling Android apps in order to monitor them or change their behavior, such as enforcing security policies that require the user to confirm sensitive actions, or to prevent network access from particular locations. In this presentation, we'll explore the relationship between these two systems by comparing their goals, techniques, and results. You can find links to both of these papers in the description of this video on YouTube. First, let's discuss some of the background of this and motivations for these papers. Most Android app stores have a very low barrier to entry, and this has led to a proliferation of apps that may be innocent-looking but leak private information, such as your phone number or contact list. And some of these apps may contain spyware or outright malware. The Android OS has a permission system where the user must approve an app's permissions at installation time. However, an app has to be approved on an all-or-nothing basis when you install it or update it. It's not currently possible to install an app but selectively disable some of its permissions. Furthermore, the permissions are not very fine-grained. For instance, internet access is an all-or-nothing permission. Either the app can connect to any site whatsoever with any protocol, or else nothing at all. All of this has led to a desire to create systems that enforce more sophisticated security policies on Android apps, in particular without needing to modify the source code of either the app or the Android. Both FireDroid and RetroSkeleton aim to do just that. They have broadly similar goals and capabilities, but they use very different techniques. They're both aimed at enforcing security policies or other behavior changes in Android apps without needing to modify their source code. However, the unique approaches taken by FireDroid and RetroSkeleton each provide a very different set of capabilities and trade-offs. RetroSkeleton works by rewriting an app into a new version that incorporates desired changes. It does this by identifying methods of interest and replacing them with calls to a policy enforcement method that may provide new behaviors or could deny the original action altogether. It then repackages all of this into a brand new replacement app that you deploy on the device as a replacement for the original app. This rewriting approach that RetroSkeleton takes has a number of advantages and disadvantages compared to other schemes like FireDroid. One huge advantage of RetroSkeleton is that it does not require any changes whatsoever to the Android operating system, whether at the source code level or at runtime. Nor does it require rooting the device or changing system files. Those are pretty big benefits because typical users don't root their phones. Also, the security policies used by RetroSkeleton are written at a very high level of abstraction and can provide completely new implementations of the targeted methods. On the con side, this solution only helps with code in the Dalvik virtual machine. Any code that uses the Native Development Kit or NDK can bypass the system. Only 5 to 10% of apps use native code, but sometimes that is used to hide malware or malicious code. Another problem for RetroSkeleton is code that is dynamically dispatched using the Java Reflection API. But one of the biggest problems with RetroSkeleton is that it creates a completely new separate app that must be used instead of the original app. This new app would not be signed by the original developer and cannot be updated from the App Store. And there's no way to force the user to use the rewritten version, and it doesn't work with any built-in system apps. So this system also requires that there is some sort of online service available to perform the app rewriting. Now, FireDroid works a bit differently. It doesn't rewrite apps at all, and it works with all existing apps, including built-in system apps and any apps that use native code. It works by taking advantage of a feature that Android inherited from the Linux kernel, which is at the heart of the Android OS. That feature is called ptrace, and it's a Linux system call that allows one process to attach to another process and trace and control its execution. The primary purpose of ptrace is to support debuggers, performance profilers, and other system tools. One of the main requirements of ptrace is that you must be the parent process of the one that you want to trace. FireDroid takes advantage of the fact that all processes on Android are launched by a master process called Zygote. FireDroid works by installing itself as the parent process of Zygote, so it can attach to it with ptrace and watch for when Zygote launches any other processes. It then makes itself the parent of those other processes, and so it can attach to them with ptrace, and once it's in control of a process with ptrace, it monitors all the system calls that are made by the app, whether directly or through some Dalvik middleware, and it can confirm or deny these operations according to a set of policies that you've specified. One of the biggest advantages of this approach is that it works with the original unmodified apps, including all built-in system apps and any apps that use native code. FireDroid doesn't require changing or recompiling the Android OS either. It only requires a small change to a plain text system config file called init.rc that controls the phone's boot process. That does mean that you need to either get root access to the phone, which is fairly simple to do, or else control the system image. For example, if you have a customized phone version that might be provided to a large corporate customer. Another benefit of this approach is that everything happens local to the device, so that there's no dependency on an external service to rewrite the apps. It's also completely transparent to any application updates from the App Store. This approach works equally well for native code, which is sometimes an attack vector for malware, precisely because the typical Android Dalvik-based security mechanism has no insight into NDK native code. Of course, this does impose some overhead. The authors found that according to a general-purpose benchmark, the prototype version of FireDroid caused a 12% performance hit and about a 3% battery life hit. Another benchmark that was more CPU-oriented found only a 1% performance hit. So like I said, FireDroid works by taking advantage of two key facts. One is that the Linux kernel at the heart of Android provides the ptrace system call, and the other fact is that all user processes on Android are launched through a master process called Zygote. By installing itself as the parent process of Zygote, FireDroid can trace when Zygote launches any other process and install itself as the parent of that process. So once it's the parent of an app process, it can attach to it with ptrace and intercept any system calls that the app makes. Now, system calls are very low level and arcane, and most apps don't make system calls directly. Instead, they call middleware using Java APIs, which eventually gets translated into system calls. FireDroid policies are written in a custom FireDroid policy language. Because they operate on system calls, FireDroid policies work at a much lower level of abstraction than RetroSkeleton. They don't offer the capability to completely rewrite operations. Instead, policy actions are limited to either allowing or denying an action, or killing the process, or prompting the user what to do, whether allow, deny, or kill. Here are some of the security applications for FireDroid that were suggested by the paper's authors, along with examples of FireDroid policy language implementations of those policies. One example is to monitor or restrict actions that might generate financial charges, such as sending SMS messages to premium numbers. This example policy sets a limit of 10 SMS messages that can be sent by an app before it must prompt the user to allow additional messages. Another example controls harvesting sensitive information, like your phone number or hardware ID. It can substitute fake numbers or prompt the user whether to allow it. The authors also describe ways to hotfix Linux kernel security vulnerabilities that might be exploited by malware. Using FireDroid, you can install a kernel security fix even before the phone vendor issues an official patch. The authors estimate that they can speed up their prototype by up to 80 times with some additional optimization work. So in conclusion, Both RetroSkeleton and FireDroid have broadly similar goals and capabilities, but they work in very different ways and have different pros and cons. RetroSkeleton doesn't require rooting the phone or changing any system files. It just rewrites an application and could potentially include completely new implementations and methods. This is a very flexible approach, but it doesn't work with native code, which is sometimes used as a malware vector. Nor does it work with built-in system apps, and there's no easy way to force the user to use the rewritten version. The types of policies and actions that FireDroid supports are rather limited compared to RetroSkeleton. However, it doesn't require any kind of app rewriting service, and it works with all types of apps, including built-in system apps and native code apps. So to summarize, FireDroid is particularly good for security policy enforcement on existing apps, but RetroSkeleton is good for rewriting apps and adding totally new behavior. Well, that concludes this presentation. Thank you for your time, and I hope you enjoyed it.